Hello, darling. Welcome. I'm so glad you're here. Tonight, we're going on a journey together, a gentle, unhurried exploration of our closest celestial neighbor. For as long as humans have looked up, the moon has been there, watching over us, lighting the darkness, marking the passage of time. It's a companion we think we know, yet it holds mysteries and wonders that might surprise you. In this cosmic journey, we'll discover 101 facts about the moon. Not as a list to rush through, but as stories to savor, ideas to contemplate, connections to feel. We'll explore how the moon was born in violence and fire. We'll walk across its ancient surface, peer into permanently shadowed craters, and venture to the far side that remained hidden for all of human history until just decades ago. We'll discover how the moon shapes Earth's tides and seasons, how it has inspired humanity's myths and dreams, and how it might become humanity's first home beyond our blue planet. To make this journey comfortable, we've divided our exploration into 8 gentle blocks, 8 chapters in the moon's story. Each one will reveal new layers of understanding, new reasons to marvel at this silvery world hanging in our sky. So settle in, take a deep breath. Let your mind drift upward, past the clouds, past the atmosphere, across the void to that ancient, patient companion. Let's begin. Close your eyes for a moment. Imagine stepping outside on a clear night. The air is cool against your skin. You look up, and there it is, our moon, hanging in the darkness like a pearl in an ocean of ink. It's been there every night of your life, sometimes full and bright, sometimes a whisper of silver, sometimes hidden entirely. But it's always there, turning slowly in the cosmic dance. Tonight, we're going to explore this ancient companion, not with haste, but with the gentle curiosity of someone leafing through a beloved book. We'll discover 101 facts about the moon, but we won't rush. Each fact is a doorway, and we'll walk through them slowly, letting the wonders settle around us like moonlight itself. The moon you see tonight is the same moon that watched over the dinosaurs. The same moon that inspired the first humans to paint on cave walls. The same moon that pulls at the oceans, that guides migrations, that has been humanity's clock and calendar for thousands of generations. It's closer to you than any other celestial body except the Suna neighbor in the vast loneliness of space. Let's begin with what we can see, what our ancestors saw, what you can witness yourself on any clear night. When you look at the moon, you're seeing something that's about 238,855 miles away from Earth on average. That might sound impossibly far, but in cosmic terms, the moon is practically in our backyard. If Earth were the size of a basketball, the moon would be a tennis ball about 23 feet away. In the grand architecture of the solar system that's intimate, the moon is the 5th largest moon in our solar system. It measures about 2,159 miles across its diameter, roughly 1/4 the diameter of Earth. If you could place it over the United States, it would stretch from coast to coast with room to spare. Yet, standing on Earth, it appears roughly the same size as the sun in our sky. A cosmic coincidence that gives us the spectacular phenomenon of total solar eclipses. That gentle glow you see isn't the moon's own light. The moon doesn't burn or shine by itself. Instead, it reflects sunlight, acting like a mirror hung in space. About 12% of the sunlight that touches the moon's surface bounces back toward Earth. This is called its albedo, and it's surprisingly lower than old asphalt or weathered concrete. The moon is actually quite dark, but against the black of space, that reflected sunlight seems brilliant. The brightness of the moon varies depending on where it is in its orbit. At its brightest during a full minute, it can be 14,000 times brighter than Venus, the next brightest object in our night sky after the sun. This brightness has guided travelers, inspired poets, and lit the night for countless generations before electric lights washed out the stars. You've noticed the moon changes shape throughout the month. These are the phases: new moon, waxing crescent, first quarter, waxing gibbous, full moon, waning gibbous, third quarter, waning crescent, and back to new. But the moon itself isn't changing. What changes is how much of the sunlit side we can see from Earth. The entire cycle, from new moon to new moon, takes about 29.5 days of lunar month. The origin of our word month, the moon's phases occur because it orbits Earth while Earth orbits the sun. When the moon is between Earth and the sun, we see the dark side of new moon. When Earth is between the moon and the sun, we see the fully illuminated face of full moon. The crescents and quarters are simply different angles of illumination, like watching someone slowly turn in a spotlight. During a full moon, you might notice patterns on its surface, dark patches and bright regions creating what looks like a face Different cultures have seen different images: a man, a rabbit, a woman, a frog. These dark areas are called Maria, the Latin word for seas, because early astronomers thought they were bodies of water. They're not. They're vast plains of ancient volcanic rock, darker than the surrounding highlands because they contain more iron and titanium. There are about 20 major Maria on the near side of the Moonaside that always faces Earth: Mare Imbrium, the Sea of Rains; Mare Tranquillitatis, the Sea of Tranquility; Mare Serenitatis, the Sea of Serenity. These names carry the poetry of old astronomers who dreamed of lunar oceans beneath Earth's watchful eye. The bright regions are the lunar highlands, older terrain covered in impact craters from billions of years of cosmic collisions. Even with the naked eye, you can see the moon isn't perfectly smooth. With binoculars or a small telescope, its surface reveals itself in stunning deep mountain ranges, valleys, and those dark Marias spreading like spilled ink. The largest crater visible from Earth is called Bailey, stretching about 183 miles across. But there are millions of craters, scars from an ancient bombardment that shaped the moon's face. The moon always shows us the same face. You've probably heard this before, but have you wondered why? It's not frozen in place. The moon does rotate, but it rotates at exactly the same rate. It orbits Earth-one rotation per orbit. This is called synchronous rotation or tidal locking, and it happened over millions of years because of gravitational forces between Earth and the moon. The moon's rotation slowed down until one side perpetually faces Earth, like a dancer forever looking at their partner. But there's a subtle wobble in the moon's dance called libration. Because the moon's orbit isn't perfectly circular and its rotation is steady while its orbital speed varies, we actually get to peek around the edges, seeing about 59% of the moon's surface over time instead of just 50%. It's as if the moon nods and shakes its head slightly, revealing glimpses of what lies beyond the edge. The moon appears larger when it's near the horizon than when it's high in the sky. This is purely an optical illusion. The moon doesn't actually change size as it moves across the sky. It's called the moon illusion. And despite centuries of study, we still don't completely understand why our brains perceive it this way. Perhaps it's because we compare the horizon moon to trees and buildings, making it seem larger while the high moon has only empty sky for reference. Sometimes the moon appears orange or red, especially when it's near the horizon. This happens for the same reason sunsets are red. The moon's light passes through more of Earth's atmosphere when it's low in the sky, and the atmosphere scatters the shorter blue wavelengths while allowing the longer red wavelengths to pass through. A harvest moon, the full moon nearest the autumn equinox, often appears particularly orange and large due to this effect combined with the moon illusion. The moon's surface temperature varies wildly because it has virtually no atmosphere to retain heat. Indirect sunlight, the surface can reach about 260 degrees Fahrenheit, hot enough to boil water. In the darkness, temperatures plummet to negative 280 degrees Fahrenheit, colder than liquid nitrogen. These extremes make the moon one of the most temperature variable places in the solar system, swinging nearly 540 degrees between day and night. A day on the moon, the time from one sunrise to the next, lasts about 29.5 Earth days, the same as a lunar month. This means 2 weeks of continuous daylight followed by 2 weeks of continuous darkness. Imagine living in a place where noon lasts for days, where shadows barely move, where sunset takes hours to complete. The moon has no atmosphere to speak of, just a thin wisp of atoms called an exoplanet. This means there's no weather on the moon. No wind, no rain, no clouds, no erosion by water or air. The footprints left by Apollo astronauts in the lunar dust will remain crisp and clear for millions of years, preserved in the airless silence like fossils of human ambition. Without an atmosphere, the sky on the moon is always black, even during the day. Standing on the lunar surface, you would see stars scattered across a dark sky while the sun blazes like a spotlight. Earth would hang in that black sky, never rising or setting if you stood in one spot, slowly going through phases just as the moon does when seen from Earth. Earth shine, Earth full Earth. From the moon, Earth would appear nearly 4 times larger in diameter than the moon appears from Earth. And because Earth has clouds, oceans, and ice, it would be much brighter, reflecting about 4 times more light. Imagine standing in the Sea of Tranquility, looking up at a brilliant blue and white marble hanging motionless in the black, knowing that everyone you've ever known, every story ever told, every human thought and dream exists on that distant sphere. These are the things we can see, the things that have been observed and wondered about for as long as humans have looked up. But how did this companion come to be? How did Earth end up with such a large, close moon? To answer that, we need to go back, far back, to a time when Earth was young and the solar system was still a violent, churning nursery of worlds. 4.5 billion years ago, give or take a few tens of millions of years, the solar system was a younger, more chaotic place. Planets were still forming, pulling together from the disk of gas and dust that swirled around the infant sun. Earth had formed, but it was nothing like the world we know. It was a molten, volcanic sphere, constantly bombarded by asteroids and other debris left over from the solar system's construction. Then something catastrophic happened, something that would change Earth forever and create the moon, the leading theory for the moons. Formation is called the giant impact hypothesis, sometimes poetically named the Big Whack or the Big Splash. According to this theory, a Mars-sized protoplanet given the name Theia after the Greek Titan, who is the mother of the moon goddess Selene, collided with the young Earth in a glancing blow. This wasn't just any collision. It was one of the most significant events in our planet's history. Theia struck Earth at an oblique angle, and the impact released more energy than 1 billion of the largest nuclear weapons ever built, all detonated at once. The outer layers of both worlds were vaporized and flung into space, creating a massive cloud of superheated rock and debris. The cores of Earth and they emerged in that cataclysmic embrace, becoming the larger core that lies at the center of our planet today. But the debris molten rock and vaporized minerals began orbiting Earth, forming a ring system much like Saturn's, but made of liquid rock, droplets, and boulders instead of ice and dust. Over time, perhaps as quickly as a few hundred years or as long as a few million, this ring of debris coalesced. Gravity pulled it together, piece by piece, into a molten sphere orbiting Earth. This was the infant moon, born from violence, glowing red hot in the darkness. Much closer to Earth than it is today, perhaps only 15,000 miles away instead of the current 240,000. The young moon was covered in a global ocean of magma, hundreds of miles deep. For millions of years, this magma ocean slowly cooled and solidified. Lighter minerals floated to the surface, forming the bright highlands we see today, while denser materials sank to form the moon's mantle and small iron core. Chemical analysis of moon rocks brought back by Apollo missions supports this impact theory. The moon's composition is remarkably similar to Earth's mantle, suggesting they formed from the same material. However, the moon has far less iron and fewer volatile elements, materials that would have been vaporized and lost during the violent formation process. The moon is also less dense than Earth, with an average density of about 3.34 grams per cubic centimeter compared to Earth's 5.5. This lower density is consistent with a body that formed primarily from the outer layers of two colliding worlds rather than from a complete planetary body. The moon's small iron core is only about 240 miles in diameter, compared to Earth's core, which extends about 2,160 miles from the planet's center. This small core is part of the evidence for the giant impact of the moon formed from the mantles of Earth and Theia, not from their iron-rich cores. In those early days, when the moon was much closer to Earth, tides were tremendously more powerful than they are today. The ocean tides might have been hundreds of feet high, surging across the young Earth's surface. These powerful tides heated the Earth's interior through friction and may have played a crucial role in the early evolution of our planet's geology. The moon was also spinning much faster initially, not yet locked into synchronous rotation. Both Earth and the moon were rotating much faster in their youth, and Earth's day might have been only 5 hours long. But the gravitational interaction between the two, the friction of those massive tides began to slow both rotations and change the moon's orbit. The moon is still moving away from Earth, even now, at a rate of about 1.5 inches per year, roughly the same rate your fingernails grow. This might not sound like much, but over billions of years, it adds up. The moon will continue to drift away, the orbital dance slowly expanding, until eventually the Earth-Moon system reaches a stable configuration billions of years in the future. In those first several 100 million years after formation, both Earth and the moon experienced what's called the late heavy bombardmenta period, when the inner solar system was pummeled by asteroids and this bombardment, which peaked around 4 billion years ago, carved most of the large craters we see on the moon today, including the giant impact basins that would later fill with lava to become the Maria. One of the largest of these impacts created the South Poetic Basin on the moon's far side, a crater about 1,600 miles across and 8 miles deep, one of the largest known impact craters in the entire solar system. This ancient scar tells of a collision so powerful it nearly broke through the moon's crust entirely. Between about 4 billion and 3 billion years ago, Volcanic activity on the moon reached its peak. Radioactive elements deep in the moon's interior decayed, producing heat. This heat melted rock in the upper mantle, and the molten rock magma found its way to the surface through cracks created by the massive impacts. The magma flooded the low-lying impact basins, creating the dark Maria we see today. These volcanic plains are made of basalt, a dark volcanic rock rich in iron and magnesium. The Maria are younger than the surrounding highlands, though younger in lunar terms still means 3 to 4 billion years old. The difference in age is visible in the crater density. The highlands are saturated with craters, while the Moria have far fewer because they formed after the late heavy bombardment had mostly ended. The moon's volcanic activity gradually declined as its interior cooled. By about 1 billion years ago, the moon had become geologically dead. No more volcanoes, no more lava flows, no more internal heat engine driving change. It became a frozen world, preserving the record of the solar system's violent youth on its surface, like a museum of deep time. The moon doesn't have tectonic plates like Earth. There's no continental drift, no mountain building through plate collisions, no subduction zones where old crust recycles into the mantle. The moon's crust is essentially one solid piece, perhaps 30 to 40 miles thick, thicker on the far side than on the near side, a difference that still puzzles science. Because the moon has been geologically inactive for so long, and because it has no atmosphere to erode its surface, the moon is like a time capsule. The ancient craters remain, the old lava flows are preserved, the record of 4.5 billion years lies exposed and readable to those who know how to read it. In a sense, studying the moon is like studying Earth's lost childhood, because Earth's active geology and erosion have erased most of its early history. The moon's formation may have been crucial for life on Earth. The impact that created the moon likely stripped away Earth's early atmosphere and delivered materials that would become essential for our planet's development. The moon's gravity stabilized Earth's axial tilt, preventing wild swings in climate that might have made the development of complex life more difficult. We are, in a very real sense, children of that ancient collision, inhabitants of a world shaped by the moon's creation. This violent birth, this cosmic accident, gave Earth its companion, and that companion, in turn, shaped Earth in profound ways that continue to this day. Let's explore the intricate dance these two bodies share, the orbital mechanics that govern their relationship, the subtle influences and rhythms that connect them across the void. The moon doesn't travel around Earth in a perfect circle. Its orbit is slightly elliptical, Anavalshapi, which means the distance between Earth and moon constantly changes. At its closest approach, called perigee, the moon is about 225,623 miles from Earth. At its farthest point, called apogee, it's about 252,088 miles away. This varying distance has noticeable effects. When a full moon occurs at or near perigee, we get what's commonly called a supermoon. The moon appears up to 14% larger and 30% brighter than when it's at apogee. The difference is subtle but real, a reminder that the moon's orbit isn't a static, unchanging path, but a dynamic, living motion. The moon completes one orbit around Earth every 27.3 days, measured relative to the background stars. This is called a sidereal month. But because Earth is also moving around the sun, it takes the moon about 29.5 days to return to the same phase A from full moon to full moon. This is called a synodic month, and it's the basis for many lunar calendars used throughout human history. The moon orbits Earth at an average speed of about 2,288 miles per hour. That's roughly 3 times the speed of sound. Yet from our perspective on Earth, the moon seems to drift serenely across the sky, a testament to the vast distances involved and the limitations of our perception. The moon's orbit is tilted about 5 degrees relative to Earth's orbit around the sun. This tilt is why we don't have a solar eclipse every new moon and a lunar eclipse every full moon. The moon has to be at or near one of the 2 points where its orbit crosses Earth's orbital plane called nodes for an eclipse to occur. These nodes slowly shift over time in a cycle that takes about 18.6 years to complete. This slow cycling of the nodes causes the moon's maximum height in the sky to vary over an 18.6-year period. Sometimes the moon climbs high in the sky at night, other times it stays lower on the horizon. Ancient observers noticed this cycle, though they couldn't explain it without understanding orbital mechanics. The synchronous rotation of the moon always showing us the same faces maintained by what's called a tidal lock. Earth's gravity created a bulge in the moon early in its history, and this bulge always points toward Earth. If the moon tried to rotate at a different rate, Earth's gravity would pull on that bulge, creating a torque that slowed or sped the rotation until it matched the orbital period. This same tidal locking is slowly happening to Earth as well, though much more gradually. The moon's gravity creates tidal bulges in Earth's oceans, and as Earth rotates, friction from these moving water bulges is slowly transferring energy from Earth's rotation to the moon's orbit. This is why Earth's rotation is gradually slowing down and why the moon is gradually moving away. About 620 million years ago, an Earth day was only about 21 hours long, and the moon was closer. Coral fossils from that time show growth patterns that record the length of days and months, providing direct evidence of this slow change in the Earth-Moon system. In about 2 billion years, if nothing disrupts the system, Earth's rotation will slow down enough that one side of Earth will always face the moon, just as one side of the moon always faces Earth now. Earth days will be about 47 of our current days long, and the moon will hang motionless in the sky for those on the near side, forever invisible to those on the far side. But this is deep future speculation. Many things could change in that vast expanse of time. The moon's gravity is about 1/6 of Earth's. If you weigh 150 pounds on Earth, you'd weigh only about 25 pounds on the moon. This weak gravity is why astronauts could bounce and hop across the lunar surface in their bulky space. It's also why the moon couldn't hold an atmosphere. Even if it had one, gases would simply drift away into space. Too energetic for the moon's weak gravity to contain. The moon's orbital velocity is carefully balanced with Earth's gravitational pull. If the moon were moving faster, it would gradually spiral outward, eventually escaping Earth's orbit altogether. If it were moving slower, it would spiral inward, eventually crashing into Earth. The moon is moving at exactly the right speed to maintain a stable orbit, though, as mentioned, that orbit is slowly expanding. There's a phenomenon called lunar libration that allows us to see slightly more than half the moon's surface over time. There are actually 3 types of libration. Libration in longitude because the moon's orbit is elliptical but its rotation is constant. Libration in latitude because the moon's equator is tilted relative to its orbit. And diurnal libration because we observe from Earth's surface, not its center, so our viewpoint shifts as Earth rotates. Combined, these librations let us glimpse about 59% of the moon's surface from Earth, though only 50% is visible at any one time. The remaining 41%, the far side, was completely unknown to humanity until 1959, when the Soviet spacecraft Luna 3 sent back the first grainy photographs of that hidden hemisphere. The moon's orbit isn't just influenced by Earth. The sun's gravity also tugs on the moon, causing its orbit to wobble and presses in complex ways over centuries. These solar perturbations have to be accounted for to accurately predict the moon's position, a challenge that occupied mathematicians for generations before computers made such calculations routine. The Earth-Moon system is sometimes considered a double planet rather than a planet-moon system because the moon is so large relative to Earth. The ratio of the moon's mass to Earth's mass is about 1 to 81, much larger than the ratios for other planets and their moons. Pluto and its moon Charon have an even more extreme ratio and are officially considered a double dwarf planet system. The center of mass of the Earth-Moon system, the barycenter, is actually inside Earth, about 1,000 miles beneath the surface. Both Earth and Moon orbit this common center of mass as they journey around the Sun. From outside the solar system, an alien astronomer might describe our world as a double planet system with a star-centered orbit, rather than simply a planet with a moon. The moon's influence on Earth extends beyond the tides. It stabilizes Earth's axial tilt, which currently sits at about 23.5 degrees, without the moon. Computer models suggest the Earth's tilt might vary wildly over millions of years due to gravitational interactions with other planets, swinging from near 0 degrees to 85 degrees or more. Such variations would cause extreme climate instability. Mars, which has 2 tiny moons that exert negligible stabilizing force, shows evidence of such axial tilt variation. Mars tilt has varied between about 15 and 35 degrees over millions of years, and some models suggest it could have swung even more wildly in the distant past. Earth's climate stability, maintained partly by the moon's steadying influence, may have been crucial for the evolution of complex life. The moon is gradually slowing Earth's rotation, but this has an interesting consequence for timekeeping. Since 1972, scientists have occasionally added leap seconds to our clocks to keep atomic time synchronized with Earth's rotation. So far, about 27 leap seconds have been added, each one compensating for the gradual slowing of Earth's spin caused primarily by lunar tides. In about 600 million years, Total solar eclipses will become impossible because the moon will be too far away to completely cover the sun's disk. We live in a special time in Earth's history when the apparent sizes of the sun and moon in our sky are nearly identical, a cosmic coincidence that gives us the spectacular sight of the solar corona during total eclipses. This orbital dance, this gravitational embrace between Earth and moon, is one of the most thoroughly studied relationships in astronomy. Yet it continues to surprise us, revealing new subtleties and connections as our instruments and understanding improve. The moon's influence on Earth is profound, shaping not just tides and time, but the very conditions that made our world habitable and stable. Now let's walk on that distant surface, at least in our imagination. Let's explore the moon's physical characteristics, its terrain and composition, the strange and beautiful landscape that awaits anyone brave enough to visit. Imagine standing on the moon. Beneath your boots is regolith, layer of loose, fragmented material covering the solid bedrock below. This isn't soil in the familiar sense. Soil on Earth is full of organic matter, living organisms, water. Lunar regolith is purely mineral powdered rock and glass created by billions of years of meteorite impacts pounding the surface into dust and fragments. The regolith varies in depth from about 10 to 60 feet deeper in the ancient highlands, shallower on the younger Maria. It's incredibly fine like talcum powder in some places, but also sharp and abrasive. Unlike Earth's sand and soil, which are rounded and worn smooth by wind and water, lunar regolith particles are angular and jagged, never having experienced the softening touch of weathering. This sharp regolith caused problems for Apollo astronauts. It clung to everything, scratched visors and seals, and proved difficult to brush off in the airless environment. Some astronauts described it as smelling like spent gunpowder when they re-entered their lunar module and removed their helmets of smell, possibly caused by the reaction of the regolith with oxygen and moisture in the cabin. The surface of the moon is covered with craters of all sizes, from microscopic pits to enormous basins hundreds of miles across. More than 300,000 craters larger than a half-mile in diameter have been identified on the near side alone, and likely millions more exist when you count the smaller ones. The entire surface is saturated with impacts upon impacts, newer craters overlapping older ones in a chaotic pattern. Crater formation happens when a meteorite or asteroid strikes the surface at cosmic velocities, often tens of thousands of miles per hour. The impact vaporizes the impactor and excavates a crater many times larger than the original object. The material thrown out the ejecta creates rays and blankets spreading across the surrounding terrain, visible as bright streaks radiating from relatively young craters. One of the moon's most prominent craters is Tycho, about 53 miles across, with rays extending for more than 900 miles across the lunar surface. These rays are visible even with binoculars as bright streaks cutting across the dark Maria. Tycho is relatively young, only about 108 million years old, so its rays haven't yet been darkened by space weathering. Copernicus is another spectacular crater, about 58 miles across, with terraced walls and a complex central peak. When Apollo astronauts described it from orbit, they called it a magnificent sight. Copernicus is perhaps 800 million years old, young enough to still show sharp details, but old enough that impacts have begun to soften its features. The largest crater on the near side is South Poetic Basin, though most of it is actually on the far side. It's about 1,600 miles across and up to 8 miles deep, one of the largest impact structures known in the solar system. The impact that created it was so powerful it may have punched through the moon's crust entirely, exposing mantle material that later solidified. The Merlot's dark, relatively smooth plains covered about 16% of the moon's surface, mostly on the near side. The largest is Oceanus Procellarum, the ocean of storms, which stretches for about 1,600 miles and contains several smaller maria within its borders. It's not actually a single impact basin, but rather a complex region of volcanic flooding. Why are there so many maria on the near side and so few on the far side? This asymmetry is one of the moon's enduring mysteries. One theory suggests the near side crust is thinner, making it easier for volcanic material to reach the surface after large impacts. The far side has a much thicker crust, perhaps 60 miles thick compared to 30 miles on the near side, which may have prevented or restricted volcanic flooding there. The moon has mountain ranges, though they formed differently than Earth's mountains. There are no tectonic plates to push mountains up through collision and folding. Instead, lunar mountains are the rims of ancient impact basins or isolated peaks created by crater formation. The Montes Apenninus range, for example, forms part of the rim of the Mare Imbrium basin and reaches heights of nearly 3 miles. The highest point on the moon is not a mountain peak, but rather a spot on the rim of Engelgart crater on the far side. standing about 33,500 feet above the moon's average radius. For comparison, Mount Everest is about 29,000 feet above Earth's sea level, making the moon's highest point slightly taller, though height is a relative concept on a body with no sea level. The lowest point on the moon is at the bottom of the South Pelican Basin, about 29,000 feet below the average radius. This gives the moon a total relief, the difference between highest and lowest points of more than 12 miles, proportionally greater than Earth's relief considering the moon's smaller size. The moon has sinuous channels called rilles, ancient lava channels, where molten rock once flowed across the surface. Some rilles are straight and may be collapsed lava tubes, while others meander like rivers. Hadley Rill, visited by Apollo 15, is about 80 miles long and in places more than 1,000 feet deep and a mile wide, a fossil river of stone that flowed billions of years ago. There are also mysterious lunar swirls, bright, sinuous markings on the surface that don't correspond to any obvious topography. They're associated with magnetic anomalies in the crust, suggesting they might be related to ancient magnetic fields that somehow protected those areas from space weathering, keeping them brighter than surrounding terrain. But their exact origin remains uncertain. Lunar caves and lava tubes have been discovered, some potentially large enough to house a small city. These tubes formed when the surface of a lava flow cooled and solidified while molten rock continued to flow beneath, eventually draining away and leaving a hollow tunnel. Such tubes could offer natural radiation protection for future lunar habitats, shielding inhabitants from cosmic rays and solar radiation. The moon has water, though not in the form you might expect. It's not flowing in streams or pooled in lakes. Instead, water ice exists in permanently shadowed craters near the poles, where temperatures never rise above about -250 degrees Fahrenheit. These cold traps have accumulated water delivered by comets and asteroids over billions of years, preserved in perpetual darkness and cold. The Lunar Crater Observation and Sensing Satellite, or LC, deliberately crashed into Cabeus crater near the South Pole in 2009. The impact plume kicked up material from the crater floor, and instruments detected not just water ice, but also other volatile compounds: ammonia, methane, mercury, sodium, and silver. These permanently shadowed craters are time capsules, preserving materials that would evaporate anywhere else on the moon. There may be as much as 600 million metric tons of water ice in the lunar poles, distributed across an area roughly the size of Mexico. This water could be crucial for future lunar bases, providing drinking water, breathable oxygen, and even rocket fuel if split into hydrogen and oxygen through electrolysis. In contrast to the frozen poles, the moon's equatorial regions can reach temperatures of 260 degrees Fahrenheit in direct sunlight. This extreme temperature range of about 540 degrees Fahrenheit from hottest to coldest is among the largest of any body in the solar system. The lack of atmosphere means there's nothing to moderate temperatures or transfer heat from hot regions to cold ones. The moon's surface is constantly bombarded by micrometeors. Over time, these impacts melt the surface of regolith particles, creating tiny beads of glass that mix with the dust. The moon's soil contains billions of these microscopic glass spheres, frozen droplets of melted rock. This process, along with radiation from the sun, gradually darkens the lunar surface over millions of years through a process called space weathering. Fresh crater ejecta appears bright because it's newly exposed material, but over time it darkens to match its surface. By studying the brightness of lunar features, scientists can estimate their relative ages. The moon's surface contains helium-3, a rare isotope of helium that's constantly deposited by the solar wind. Helium-3 is extremely rare on Earth, but could potentially be used as fuel for fusion reactors. If we ever develop that technology, some have proposed mining the moon for helium-3, though this remains far in the future and controversial. Titanium is abundant in some lunar maria, particularly Mercury, where concentrations are higher than anywhere on Earth's surface. The moon also contains abundant aluminum, silicon, and oxygen, the materials needed to produce metals, glass, and even rocket fuel using in situ resource utilization. The moon could, in theory, provide most of the materials needed to build and sustain a permanent lunar settlement. Lunar soil is electrostatically charged by solar radiation, causing the fine dust particles to levitate slightly and cling to surfaces. This electrical charge made the dust particularly troublesome for Apollo missions, as it stuck to spacesuits and equipment, despite attempts to brush it off. Understanding and mitigating lunar dust will be crucial for future long-term lunar operations. The moon has no global magnetic field today, but rocks brought back by Apollo missions show that ancient lunar rocks formed in the presence of a magnetic field. This suggests the moon once had an internally generated magnetic field, similar to Earth's, but it died away between about 4 billion and 1 billion years ago as the moon's core cooled and solidified. Some regions of the moon still have localized magnetic anomaly spots where the crust retains magnetization from ancient times or from nearby large impacts. These magnetic anomalies can deflect solar wind particles, creating small protective bubbles in the stream of charged particles constantly flowing from the sun. This strange, airless, waterless, magnetically dead world is Earth's companion. Its surface tells stories written over billions of years in stone and dust. And this surface, this ancient witness, has profound effects on Earth itself, effects that reach across the void between the two worlds and touch every ocean. Every coastline, every living thing that depends on the rhythms of tide and time. Stand on any ocean beach and watch the water advance and retreat. Twice each day, the ocean rises up the shore, then withdraws. Twice each day, this ancient rhythm repeats. You're watching the moon's most obvious gift to Earth, the tides. The moon's gravity pulls on Earth, but it doesn't pull evenly. The side of Earth facing the moon feels a slightly stronger pull than Earth's center, and Earth's center feels a stronger pull than the side facing away from the moon. This difference in gravitational force, called the tidal force, stretches Earth very slightly into an oval shape. Water, being fluid, responds most visibly to this stretching. The oceans bulge slightly toward the moon and slightly away from it on the opposite side of Earth. As Earth rotates beneath these bulges, any given location experiences to high tides and to low tides roughly every 24 hours and 50 minutes, the extra 50 minutes accounting for the moon's own motion around Earth. The sun also creates tides, but solar tides are about 43% as strong as lunar tides, despite the sun's vastly greater mass. Distance matters. The moon is much closer, and tidal force drops off rapidly with distance proportional to the cube of the distance, not just the square. Proximity trumps mass when it comes to tides, when the sun, moon, and Earth align during new moon or full moon. Solar and lunar tides combine to create spring tides, the highest high tides and lowest low tides of the month. When the sun and moon are at right angles during first and third quarter moons, their tidal effects partially canceled, creating neap tides, the most moderate tides of the month. This pattern repeats every month, a cosmic metronome that has kept time for billions of years. The largest tides on Earth occur in the Bay of Fundy in Canada, where the unique shape and depth of the bay amplify tidal effects. Water levels there can change by more than 50 feet between high and low. You'd imagine a 5-story building appearing and disappearing twice each day. This enormous movement of water has been harnessed to generate electricity at some tidal power plants. But tides aren't just about oceans. The moon also creates tides in Earth's atmosphere, atmospheric tides, that subtly affect air pressure and winds. These atmospheric tides are much smaller than ocean tides, but they're real and measurable. Even Earth's solid crust experiences tides, bulging up and down by about a foot as the moon passes overhead, though we don't notice because everything around us moves together. These tidal forces create friction as Earth rotates and the tidal bulges try to stay aligned with the moon. Friction primarily from water moving across the ocean floor converts some of Earth's rotational energy into heat. This friction is gradually slowing Earth's rotation, making our days incrementally longer, as mentioned earlier. Simultaneously, this tidal friction transfers energy to the moon's orbit, causing the moon to gradually spiral outward. The system loses rotational energy but gains orbital energy, conserving the total angular momentum of the Earth-Moon system. It's an elegant example of physics in action, visible in the slow drift of the moon and the lengthening of our days. The moon's gravitational pull may trigger earthquakes on Earth, though this remains somewhat controversial. Some studies suggest that when tidal forces are at their peak during new or full moons, they can provide just enough additional stress to trigger earthquakes on faults that are already near failure. The moon doesn't cause earthquakes, but it might occasionally provide the final push that sets them off. The moon definitely triggers moonquakes, seismic activity on the moon itself. Moonquakes fall into 4 categories. Deep moonquakes about 400 miles below the surface, caused by tidal forces from Earth. Shallow moonquakes, which can register up to 5.5 on the Richter scale. Thermal moonquakes from the expansion and contraction of the surface as it heats and cools. And impact moonquakes from meteorite strikes. Deep moonquakes occur in patterns linked to the moon's distance from Earth, demonstrating that Earth's tidal force can trigger seismic activity deep within the moon just as the moon's tidal force might trigger some earthquakes on Earth. It's a mutual gravitational conversation, written in shifting stone and trembling ground. The moon's influence on Earth's axial tilt is perhaps its most profound and least appreciated effect. Earth's axis is tilted at about 23.5 degrees relative to its orbit around the sun. This tilt gives us our season summer when our hemisphere tilts toward the sun, winter when it tilts away. But that tilt is stable because of the moon. Without the moon, gravitational interactions with Jupiter and other planets would cause Earth's axial tilt to vary chaotically over millions of years. Computer simulations show that a moonless Earth might wobble between 0 and 85 degrees of tilt. Imagine seasons so extreme that the poles experience months of direct overhead sun while the equator freezes, then reversing over geologic time. Such climate instability would make the evolution of complex life far more difficult. The moon acts as a stabilizer, a gravitational anchor keeping Earth's tilt within a narrow range varying only between about 22.1 and 24.5 degrees over a 41,000-year cycle. This stability has been crucial for Earth's climate predictability over the hundreds of millions of years required for complex life to evolve. The moon's light itself has biological effects. Many organisms have evolved behaviors synchronized to the lunar cycle. Sea turtles use the moon to navigate, and many species of fish, crabs, and other marine life time their spawning to lunar phases. Coral reefs often spawn in mass events synchronized to full moons, releasing eggs and sperm into the water in coordinated timing that increases reproductive success. Some animals use moonlight for navigation. Moths and other insects use the moon as a compass, maintaining a constant angle to its light to fly in a straight line, which is why artificial lights confuse them, causing them to spiral as they try to maintain that angle to a nearby light source instead of the distant moon. Relationships are influenced by moonlight. Nocturnal predators hunt more successfully during bright moonlit nights, while prey species often reduce activity during full moons to avoid predation. This dynamic has shaped countless evolutionary adaptations over millions of years. Human cultures have synchronized their lives to the moon for millennia. Most early calendars were lunar calendars, based on the moon's phases. The Islamic calendar still is purely lunar, with 12 lunar months adding up to about 354 days. The Jewish and Chinese calendars are lunisolar, adding occasional extra months to keep synchronized with solar season. The English words month and Monday both derive from moon. The Latin word mensis, month, is related to meaning moon, and connects to menstruation, which has an average cycle length similar to the lunar month, though there's no proven causal connection, despite ancient beliefs otherwise. The moon has been used for navigation throughout human history. Before compasses and GPS, sailors used the moon's position and phase to estimate time and direction. The moon's predictable motion across the sky provided a reliable reference point, especially important when the sun was below the horizon. Lunar eclipses, when Earth's shadow falls on the moon, have been used to measure longitude and synchronize clocks across vast distances. In the 18th and 19th centuries, astronomers would calculate when eclipses would occur and observe their timing from different locations, using the time difference to determine longitude. The moon affects human culture in ways beyond practical timekeeping. Full moons have been associated with madness, hence the word lunacy, from the Latin luna. While careful statistical studies have found no actual correlation between lunar phases and mental health, crime rates, or hospital admissions, the belief persists, a cultural fossil from ancient times. The moon has inspired countless works of art, literature, music, and film. It represents romance, mystery, transformation, cycles, and the boundary between Earth and the cosmos. It's a universal symbol understood across cultures, appearing in myths and stories from every corner of the world. The gravitational relationship between Earth and Moon has given us something precious and stable: predictable world with moderate seasons, reliable tides, and a bright companion in the night sky. We are shaped by the moon in ways we rarely consider, living in its influence as fish live in water. So constant and pervasive that we notice it only when we stop to look. But there's more to the moon than the face we see. There's a hidden hemisphere, turned forever away from Earth, unknown to humanity until the space age. Let's venture beyond the familiar near side and explore the mysteries that lie on the far side and deep within. For all of human history until 1959, no one had ever seen the far side of the moon. It wasn't mysterious in the sense of being unknowable. Astronomers understood why one hemisphere always faced Earth, but it was simply invisible, hidden by the moon's synchronous rotation. We could only imagine what lay on that eternally averted face. Then, in October 1959, the Soviet spacecraft Luna 3 swung around the moon and transmitted the first grainy, crude images of the far side back to Earth. What those images revealed was surprising. The far side looked dramatically different from the near side, where the near side has vast dark Maria covering about a third of the visible hemisphere. The far side is almost entirely Bright Highlands ancient, heavily cratered terrain with only a few small Maria. The largest feature on the far side is the South Poleitkin Basin, that enormous ancient impact crater mentioned earlier, one of the largest in the solar system. Why this asymmetry? Why are the hemispheres so different? This question has puzzled scientists for decades, and we still don't have a complete answer. One factor is crustal thickness. The far side crust is significantly thicker than the near side, perhaps because when the moon formed, the near side faced the still molten Earth and stayed warmer, preventing the crust from growing as thick. This thicker crust may have made it harder for volcanic magma to reach the surface on the far side even after large impacts. When asteroids punched through the thinner near side crust, magma could flood up and fill the impact basins. But on the far side, most impacts didn't penetrate deeply enough through the thicker crust to tap the magma sources below. So the craters remained unfilled. Another theory involves the moon's internal structure. The moon's center of mass is actually offset from its geometric center by about 1.2 miles toward Earth. This offset might have influenced how the moon responded to impacts and how Izeli volcanic material could reach different parts of the surface. Recent research has even suggested that Earth itself might have influenced the asymmetry. In the moon's early history, when it was much closer to Earth and both bodies were still partially molten, heat from Earth could have affected how the moon's crust formed and evolved. The near side, facing Earth, might have experienced different cooling and volcanic activity than the far side. The far side of the moon is sometimes incorrectly called the dark side, but this is the far side receives just as much sunlight as the near side over the course of a lunar day. During a new moon, the far side is actually fully illuminated while the near side is dark. Dark in this context means unknown, hidden dark in the sense of mystery, not the absence of light. One of the strangest features on the moon is the far side's collection of magnetic anomalies, localized regions of magnetic field much stronger than the moon's general background. These are fossil magnetism locked into rocks when the moon had a global magnetic field billions of years ago. But their distribution is puzzling, and we don't fully understand what geological processes created such strong local magnetization. The interior of the moon is another realm of partial knowledge and ongoing mystery. We know the moon has a small iron core, about 240 miles in diameter, surrounded by a partially molten layer, then a solid mantle, and finally the crust. But our knowledge of the deep interior comes primarily from seismic data collected by Apollo missions decades ago and from careful analyses of the moon's gravitational field. The moon's small core suggests it formed from the outer layers of colliding bodies rather than from complete planetary bodies with large iron cores. The core is probably partially molten, based on its effects on how the moon responds to Earth's tidal forces. Modern analysis of old Apollo seismic data, using techniques unavailable when the data was first collected, continues to reveal new details about the moon's internal structure. The moon experiences moonquakes, as mentioned earlier, but they're very different from earthquakes. Deep moonquakes can last for more than 10 minutes, compared to just a few minutes for most earthquakes. This is because the moon's interior is much drier and colder than Earth's, so seismic waves don't dissipate as quickly. The moon rings like a bell when struck, reverberating for hours. One of the ongoing mysteries involves the moon's heat flow. The moon generates internal heat through radioactive decay of elements like uranium, thorium, and potassium in its interior. But measurements of heat flow from the moon's interior show regional variations that aren't fully explained. Some areas release more heat than expected, others less, hinting at internal structure we don't yet understand. The moon has mass concentrations called maskins beneath some of the large impact basins. These are regions of unusually dense material that create stronger local gravity. They were discovered when they affected the orbits of spacecraft circling the moon, causing small but measurable changes in orbital speed. Mascuns are probably the dense basaltic lava that filled the impact basins, but their exact structure and origin remain subjects of study. There are strange light phenomena on the moon called transient lunar phenomena, or TLP's brief flashes of light, glows, or color changes observed from Earth. These reports go back centuries, long before the space age. Most TLPs are probably misidentifications, observation errors, or atmospheric effects, but a small percentage remain unexplained, possibly representing outgassing events where volatiles trapped beneath the surface occasionally escape. The moon's surface is subtly radioactive. Cosmic rays and solar particles constantly bombard the surface, creating secondary radiation and radioactive isotopes. The Apollo missions left instruments on the surface that measured radiation levels, important information for planning future crewed missions. Astronauts will need protection from this radiation, either through shielding or by spending most of their time in underground habitats. We still don't fully understand how much water exists on the moon or where it all came from. The permanently shadowed craters at the poles clearly contain water ice, but recent observations suggest there might also be water molecules bound to minerals in sunlit regions. Protected from evaporation by being chemically bound or hidden in the crystal structure of rocks, some of this water might be produced constantly by the interaction of solar wind hydrogen ions from the sun with oxygen in lunar rocks, creating hydroxyl and water molecules. Other water was delivered by comets and water-rich asteroids over billions of years. Distinguishing between these sources and understanding the moon's total water inventory is an active area of research. The moon's gravity field isn't perfectly uniform. Spacecraft orbiting the moon experienced slight variations in gravitational pull that revealed density differences in the crust and subsurface. Mapping these variations helps scientists understand the moon's internal structure and geological history, but some gravity anomalies remain puzzling, hinting at structures or compositions we haven't fully explained. There is a question about the moon's early magnetic field. How did such a small body generate a magnetic field strong enough to magnetize rocks? On Earth, the magnetic field is generated by convection in the liquid iron outer core dynamo effect. The moon's core is much smaller, and it's unclear whether it could have sustained the same type of dynamo. Some scientists have proposed alternative mechanisms, but this remains an open question. Another mystery involves the timing of the moon's volcanic activity. Why did volcanic eruptions continue for so long on such a small body? Small worlds should cool quickly and become geologically dead early in their history. Yet the moon had volcanic activity for billions of years. Was there a heat source we haven't identified? Or did the moon's interior composition allow it to retain heat longer than simple models predict? The lunar swirls, those mysterious bright markings associated with magnetic anomalies, have no consensus explanation. One theory suggests they're areas where fossil magnetic fields deflected solar wind particles, protecting the surface from space weathering that would normally darken it, but this doesn't explain all their characteristics. Other theories involve unusual dust deposition or exotic volcanic processes. The swirls remain one of the moon's most visually striking mysteries. Recent evidence suggests the moon might have had periods of volcanic activity more recently than previously thought, as recently as 100 million years ago, rather than 1 billion years ago. If confirmed, this would force a revision of our understanding of lunar thermal evolution. Why would the moon's interior stay warm enough for volcanic activity so long? These mysteries remind us that despite centuries of observation and decades of direct exploration, the moon still holds secrets. It's not a solved puzzle, not a completely known world. Each answer reveals new questions. Each discovery suggests phenomena we hadn't imagined. The moon is familiar but not fully known, like an old friend who still surprises you. This mysterious ancient companion has drawn humanity's eyes and dreams skyward for all of recorded history. And eventually, those dreams became reality. We reached out across the void, built machines that could survive the journey, and finally set foot on that distant shore. Let's explore humanity's relationship with the moon, from ancient myths to modern missions. Before telescopes, before science, before recorded history, humans looked at the moon and told stories. The moon appeared in the mythology of every culture: a goddess, a god, a celestial being, a realm of the dead, a mirror, a doorway, a wanderer, a watcher. In ancient Mesopotamia, the moon god Sin was one of the most important deities associated with wisdom and the passage of time. The Greeks saw Selene, the moon goddess, driving her chariot across the night sky. The Romans called her Luna. In Chinese mythology, change lives on the moon, accompanied by a jade rabbit. Hindu tradition speaks of Chandra, the moon god. These stories span cultures and continents, united by the same bright presence in the night sky. The moon's phases were noticed and recorded by ancient peoples. Stonehenge and other megalithic structures show alignments to lunar events, suggesting that Neolithic people tracked lunar cycles thousands of years ago. The Babylonians developed sophisticated mathematical models to predict lunar eclipses. Ancient astronomy was largely lunar astronomy. The invention of the telescope in the early 17th century revolutionized lunar observation. Galileo Galilei was among the first to turn a telescope skyward in 1609, and he was astonished by what he saw. The moon wasn't a perfect sphere, but had mountains, valleys, and craters. It was a world not just a light in the sky. His drawings and descriptions challenged the prevailing Aristotelian view that celestial bodies were perfect and unchanging. Giovanni Riccioli created one of the first detailed lunar maps in 1651 and established the naming convention we still use today, creators named after scientists, philosophers, and scholars. Maria given Romantic Latin names. This tradition continues, with new features discovered by spacecraft receiving names approved by the International Astronomical Union. As telescopes improved, lunar cartography became increasingly detailed. By the 19th century, selenographers, mapmakers of the moon, had charted the visible hemisphere in great detail, naming thousands of features, but they could only see one side. The far side remained completely unknown, a blank space on the map. The space age began in 1957 with Sputnik, and the moon quickly became a target. The Soviet Union's Luna 2 became the first human-made object to reach the moon in 1959, impacting the surface. Luna 3, launched the same year, provided those first astonishing images of the far side. The moon race had begun. Throughout the early 1960s, both the United States and Soviet Union sent missions to the moon. Rangers, surveyors, orbiters, and more. Lunas flew, crashed, orbited, landed softly, and sent back thousands of photographs. Each mission revealed more detail, more information, preparing for the ultimate goal, landing humans on the lunar surface. President John F. Kennedy's 1961 announcement that America would land a man on the moon before the decade's end was as much political as scientific, a Cold War competition, a demonstration of technological prowess, but it captured global imagination. The moon became not just a distant object, but a destination, a place humans would actually visit. The Apollo program sent 9 missions to the moon, 6 of which landed successfully, putting 12 human beings on the lunar surface between 1969 and 1972. Apollo 11's landing on July 20th, 1969 was watched by millions around the world. Neil Armstrong's words, "That's one small step for man, one giant leap for mankind," entered the lexicon of human achievement. The Apollo astronauts spent a total of about 300 hours on the lunar surface across all missions. They drove lunar rovers across the regolith, conducted experiments, collected rock samples, took photographs, and described what they saw, their observations, and the 842 pounds of moon rocks they brought back, transformed our understanding of the moon's composition, age, and history. Those moon rocks provided evidence for the giant impact theory of lunar formation. They revealed the moon's ancient age, some samples dating back for 0.4 billion years, nearly as old as the solar system itself. They showed the moon is largely dry, with negligible amounts of water locked in minerals, though we now know ice exists in polar cold traps. The Apollo missions left behind scientific instruments that continued operating for years after the astronauts departed. Seismometers measured moon laser reflectors, mirrors that bounced laser beams. Back to Earth allowed precise measurement of the Earth-Moon distance and continue to be used today. These experiments provided data about the moon's interior structure and orbital dynamics that couldn't be obtained any other way. Apollo 17 1972 was the last crewed mission to the moon. Since then, humans have not ventured beyond low Earth orbit. The moon has been studied by robotic missions Clementine, Lunar Prospector, Chandrayaan Change, the Lunar Reconnaissance Orbiter, and others, but no human has set foot there in more than 5 decades. This gap seems strange now. We went to the moon 6 times in 3 years, then stopped. The reasons were political and economic. The Cold War motivation diminished, public interest waned, budgets tightened, space exploration shifted focus to Earth, orbit, planetary probes, and eventually the International Space Station. But interest in lunar exploration is NASA's Artemis program aims to return humans to the moon, including the first woman and first person of color, potentially as soon as the mid-2020s. The goal isn't just to visit, but to establish sustainable exploration, creating bases and infrastructure that could support long-term human presence. Other nations are pursuing lunar programs. China has landed robotic missions on the lunar surface, including Change 4 on the far side in 2019, the first soft landing there. China has announced intentions to build a lunar base in cooperation with Russia. India, Japan, South Korea, and the European Space Agency all have active or planned lunar missions. Private companies are also targeting the moon. SpaceX is developing Starship partly for lunar missions. Several companies are working on lunar landers and rovers. The moon is increasingly seen not just as a destination for exploration, but as a resources source of water, metals, and potentially helium-3, and a staging ground for missions deeper into the solar system. The moon has become a proving ground for international space law. The Outer Space Treaty of 1967 declares that outer space, including the moon, cannot be claimed by any nation and should be used for peaceful purposes. But as commercial lunar activities become realistic, questions arise about resource ownership, property rights, and governance. These questions will likely shape lunar exploration in coming decades. Humans left a lot behind on the moon. 6 American flags, though they've likely been bleached white by decades of unfiltered solar radiation. Plaques, photographs, golf balls, scientific instruments, and yes, 96 bags of human waste astronauts had to lighten their lunar modules before takeoff. All of this remains on the airless surface, an archaeological site from humanity's first venture to another world. There are also memorials. The Falam, astronaut sculpture and plaque at the Apollo 15 landing site, commemorates astronauts and cosmonauts who died in the pursuit of space exploration. A small silicon disc containing messages from world leaders sits on the moon. These artifacts connect the moon to human history, making it not just a celestial object, but a place where humans have been, a place marked by our presence. The cultural impact of lunar exploration is immeasurable. The images of Earth rising above the lunar horizon, taken by Apollo 8 astronauts on Christmas Eve 1968, helped inspire the environmental movement by showing our planet's fragility and isolation. The moon landings demonstrated what humans could achieve through determination. Science, in cooperation, a counterpoint to the conflicts and divisions that marked the 20th century. Children around the world grew up watching those grainy black and white images of astronauts bounding across the lunar surface. A generation was inspired to become scientists, engineers, and explorers. The moon went from mythological symbol to actual place, a transition that fundamentally changed how humans view themselves and their place in the cosmos. Yet most people alive today weren't born when humans last walked on the moon. For many, lunar exploration is history, not current events. The moon has receded from immediate consciousness even as our knowledge of it has grown. But perhaps that's about to change. As new missions launch and new plans develop, the moon is coming back into focus. Not as a destination visited and abandoned, but as a neighbor we're learning to live with. What might the future hold for the moon and humanity's relationship with it? Let's look ahead, imagining what could come in the next decades and centuries as we close our journey through these 101 facts. Imagine years from now watching a live video feed from the moon, not a brief visit, but a permanent presence, a lunar base where people live and work for months at a time. This isn't science fiction. It's the direction multiple space agencies and private companies are working toward. The moon is about to become not just a place we study, but a place we inhabit. NASA's Artemis program plans to establish a base called Artemis Base Camp near the lunar South Pole. This location was chosen carefully. The South Pole has areas of near-permanent sunlight on crater rims, providing almost constant solar power and permanently shadowed craters containing water ice nearby. It's one of the few places on the moon where you could access both energy and water resources relatively easily. The base wouldn't start large. Initial missions might involve habitats that astronauts stay in for days or weeks. Gradually, the infrastructure would expand power systems, landing pads, storage facilities, laboratories. Over time, crews might stay for months, conducting research and learning to use lunar resources to support themselves. Mining water or ice from the polar cold traps could provide drinking water, oxygen for breathing, and hydrogen and oxygen for rocket fuel. If future lunar bases can produce their own launches from the moon to other destinations become much more efficient than launches from Earth, because the moon's gravity is so much weaker, the moon could become a way station for missions to Mars and beyond. Assembling spacecraft on the moon or in lunar orbit, fueling them with propellant produced from lunar resources, would make deep space exploration more sustainable. The moon becomes not an endpoint, but a beginning, a first step outward. Several countries and companies are developing lunar landers and cargo systems. These won't just carry astronauts, but also equipment, supplies, and construction materials. Building on the moon will require new techniques, perhaps 3D printing structures using lunar regolith as raw material, or inflatable habitats protected by regolith shielding from radiation. Some proposals envision using lunar lava tubes, those natural caves formed by ancient lava flows, as ready-made shelter. A lava tube large enough to house a small city would provide natural protection from radiation, micrometeorites, and temperature extremes. You'd seal the ends, pressurize the interior, and have a spacious habitat with kilometers of interior space. Tourism might eventually come to the moon, though it will likely remain expensive for the foreseeable future. SpaceX's founder Elon Musk has spoken of sending people around the moon on Starship. Japanese billionaire Yusaku Maezawa has booked such a flight. Others may follow. The idea of tourists visiting the moon, even just orbiting it, seemed absurd a decade ago, but now appears increasingly possible. The moon's lack of atmosphere makes it an ideal location for certain types of telescopes. An optical telescope on the far side would be shielded from Earth's radio noise and light pollution, providing pristine observing conditions. Radio telescopes on the far side could observe frequencies blocked by Earth's ionosphere, opening new windows on the universe. Lunar astronomy could revolutionize our understanding of the cosmos. Mining operations on the moon remain speculative but possible. Beyond water ice, lunar regolith contains metals like aluminum and titanium. Some envision robotic mining operations extracting and processing these materials, either for use on the moon or for export to Earth orbit, where they'd be valuable for constructing space stations or spacecraft. The extraction of helium-3, deposited by the solar wind over billions of years, has been proposed as a potential lunar resource. Helium-3 could fuel fusion reactors if that technology matures, providing clean energy. However, this remains highly speculative. We don't yet have working fusion reactors, and the economics of lunar mining are unclear. One intriguing idea involves creating a genetic backup of Earth's biosphere on the moon. A lunar ark could store seeds, DNA samples, and digital libraries as safeguard against catastrophic events on Earth. The moon's geologically stable environment and lack of atmosphere means such an archive could remain intact for millions of years. The moon might become a laboratory for understanding how to live on other worlds. Lessons learned from building and maintaining lunar habitats dealing with radiation, dust, resource extraction, closed-loop life support would apply to Mars and beyond. The moon is a testing ground, close enough to resupply or evacuate if necessary, far enough to pose real challenges. There are also proposals for lunar power stations. Solar arrays on the moon could collect sunlight and beam energy to Earth using microwaves or lasers. The moon's long lunar day and absence of clouds or atmosphere make it attractive for solar power generation, though the engineering challenges of transmitting power across space are immense. In the much longer-term centuries or millennia from now, some futurists imagine the moon could be transformed through terraforming. Could the moon ever have an atmosphere? Could it hold water on its surface? These questions venture into speculation. The moon's low gravity makes holding an atmosphere difficult, though not impossible with sufficient replenishment. Such projects, if even possible, would require capabilities far beyond anything we currently possess. More realistically, the moon might develop a permanent population numbered in hundreds or thousands over the next century or two. These lunar inhabitants would be scientists, engineers, technicians, and eventually perhaps families. Children born on the moon would be the first humans for whom Earth was the foreign world, not home. They would grow up in 1/6 gravity, able to jump 6 times higher than on Earth, seeing Earth as a blue ornament in their black sky. The political and legal frameworks governing the moon will evolve. Who owns resources extracted from the moon? Who governs lunar settlements? How do we preserve historically significant sites like the Apollo landing areas? These questions don't yet have clear answers. International cooperation will be essential to ensure the moon benefits all humanity, not just those with the resources to get there first. The moon will always remain geologically it's too small and cold to restart volcanic activity or develop tectonic. But it could become biologically alive, carrying Earth life to a place life never reached naturally. Greenhouses growing food, bacteria recycling waste, perhaps even small ecosystems contained within sealed habitats. Life would be imported, carefully controlled, but it would be there nonetheless. Standing on the moon, a future astronaut might look at Earth rising above the horizon and feel something similar to what Apollo astronauts felt at seeing home from the outside. Wonder at the delicate beauty of our blue world hanging in the void. But they might also look at the lunar horizon and see lights the glow of a habitat, the beacon of a landing pad, signs of human presence in a place that was empty and silent for billions of years. The moon's story is our story, from its violent birth in a planetary collision, through billions of years of silent witness, to humanity's first tentative steps on its surface, to a possible future as humanity's first true home beyond Earth, the moon, and humanity's destinies are intertwined. We started by looking at the moon with naked eyes, seeing patterns of light and shadow, telling stories. We built telescopes and saw a world. We sent robots and learned its composition. We sent humans and touched it directly. Now we look ahead to living with the moon, not just visiting it. Each phase of this relationship has deepened our connection to this ancient companion. The moon reminds us that we're part of something larger than ourselves, larger than Earth. We're participants in a cosmic story that began with the Big Bang and continues through the formation of galaxies, stars, planets, and moons. The moon is a chapter in that story, and so are we. When you look at the moon tonight, whether it's a thin crescent or a full disk, whether it's high in the sky or hanging near the horizon, remember that you're looking at a world with mountains and valleys, craters and plains, ice and stone, a world that has shaped Earth and will shape humanity's future, a world that's both utterly alien and intimately familiar. The moon has been with Earth for 4.5 billion years. It will be here for billions more, long after individual human lives, cultures, and civilizations have come and gone. But for this brief moment in cosmic time, we're here together, Earth, moon, and humanity connected across the void by gravity, light, and curiosity. Sleep well, knowing that the moon keeps watch. And perhaps somewhere in your dreams, you'll find yourself standing on that gray surface, looking back at Earth, seeing home from a distance and understanding in that moment how precious and rare our world truly is. If you enjoyed this journey through the moon story, consider subscribing and sharing this with someone who loves the night sky. The cosmos has many more stories to tell, and we're just beginning to listen. Good night, and look up.